Hi, welcome. I hope you're doing well on your TOEFL test. Taking it right now as we speak. Just remember that the plural of box is boxes and not boxing. Let's see here. So we're going to justify the procedure that we've been calling the argument from the sign of f prime. We're going to do that by examining what happens at the endpoints of domains. So our theorem is going to be this. If f prime is positive for x less than c, and f prime is negative for x greater than c, then f of c is the absolute max of f. And the absolute min, if any, occurs at an endpoint. So this is the theorem that lies at the back of our argument from the sign of f prime. To see why this is true, let's have a little theorem that is going to help us, and our helper theorem is going to be this. If f prime is positive on the interval a to b, notice that b is closed here, a is not. Then f of b is the absolute max on that interval. Intuitively, this is simple. Because f is increasing, then from a to b, it's clear that f of b has to be the biggest point. Graphically, it's clear. The only thing that causes us a little bit of hesitation is that b is the endpoint of the interval, and we only have a theorem that guarantees that f is increasing in the full interval. So what we're really trying to do with our limit is to include that endpoint now and see what happens. The proof is going to be pretty simple. Take any x. Wow. Try again. Take any x in the open interval a to b, and f is continuous on x to b because it is differentiable on that interval, and f is differentiable because it is differentiable, and therefore, what can I conclude from these two facts? Say that again, Bob. So what does f prime of c have to equal to? We don't have f of x equals f of b, so Raleigh's theorem doesn't apply. Hence Raleigh's theorem on its side. Yeah. So give me the conclusion. Well, yeah, there are no a is not. Yeah. So the thing to check here was, do we have f of x equals f of b? If so, we can go to Raleigh. Otherwise, we generalize it to mean value. And in fact, a lot of books, this book included, does not even teach Raleigh's theorem. It just has you do mean value, and then Raleigh's theorem will be a special case of that. But they can only do that if they provide mean value theorem calculation. Okay? Now, what can we conclude about this? What we're trying to get to is that f of b is the absolute max here, which would be true if f of b is bigger than all of the f of x's. Is that so? Well, we know that f of c is positive, and we also know that b minus x is positive because b is the right-hand endpoint of that interval. And therefore, I can multiply both sides by b minus x and get that f of b minus f of x is a positive number. So f of b is bigger than f of x for every single x value in the interval a to b, which means it is the max. And that's it. There have been a lot of theorems and proofs kind of coming at you this week, so I recognize all that. The most important theorem, the central one for this week, is the mean value theorem. And so I want to encourage you to look for opportunities to use that when you can. And if you can do that, then all the others kind of flow from that. Okay, so having done that, we now consider the proof of our theorem. And it's pretty simple. If f is defined on some interval, and we don't really care if it's an open or closed interval, let's just call it an open interval a to b, but it might be closed, and a or b might be infinity or negative infinity. And f prime of x is positive for x less than c, and f prime of x is negative for x greater than c. We're now going to take our whole interval from a to b, like so, and we're going to split it right at c. So what we have here are two different subintervals, one with a positive derivative, one with a negative derivative. And using our lemma, and the corollary to the lemma would be that if my function has a negative derivative on this interval, then f of c has to be the max here. So we have f of c is the max on the interval a to c, and f of c is also the max on the interval c to b. And because it is the largest on both of those intervals, it is therefore the largest on the whole thing united. And then we're done. The value of this proof is not found really in the details, because the details are just bookkeeping. The value of the proof is found right here in the picture. If this is my f prime number line, it is pretty self-evident that if my function is increasing and then decreasing, then f of c has to be max. And all of this stuff is just trying to get there.
Isn't just max should be in A to C as
It is a to c for the first interval, and then for the second interval, it is c to b because my derivative is negative. So same kind of argument. I didn't create a second lemma for it, but it's the same kind of argument, but using the interval c to b. Okay? And there you go. Okay, now how do we actually use this? Well, let's take a look at the question that troubled Kenneth. This was number 36 on page 226. Find the volume of the largest right circular cone. Circular. That can be inscribed in a sphere of radius 3. I'm going to generalize and just make it inscribed in a sphere of radius r. And then they provide us with a picture. So, and we put ourselves a cone, like so, and there it is. I think this one is the place. That's it. And so the question now is how to accomplish this. So we're going to do an argument from side to time, and we're going to need to go take our diagram and mark it up. Any ideas? What quantities can I relate? Radius, absolutely. And where can I draw the radius? A lot of choices.
Maybe from the middle.
All right. So this gives me an R. Good. Okay, that's a good start. I'm looking for the volume of the largest right circular cone, and so that. What's that? They do, and I'm just taking it as R. So I'm generalizing this guy. Maybe I'll do it as capital R so we don't confuse it with the formula. All right, and now we want a volume, so my volume for my cone is... And where is the R that we're talking about for the cone? Yeah, so the one thing we want to be careful about is that the R for the cone is not the same as the radius of the sphere. And where is the height h on my diagram? And all the way down like that. Good. So I can see all of this, and I can see all of this, but it's obvious that I need another equation to relate R and H together, and it's not yet obvious how I'm going to get that. So I'm going to look for opportunities to actually do that, create another equation. And the opportunities that I look for are Pythagorean theorem, similar triangles, trigonometry. Really those three things. Pythagorean theorem. Do I see any right triangles? Yeah, there's a right triangle that happens right here. Unfortunately, that would introduce a third unknown quantity, so that's not so good. But I'm not done yet, because I realize that in a sphere, everywhere you go, there's a radius. And in particular, from right here in the center down to the sphere, I have a radius of big R. And now I can do Pythagorean theorem if I simply identify the length of this side. What is the length of that side right there? Yeah, it's h, take away the radius r. And so my additional equation is therefore that h minus r squared plus r squared is equal to the big R squared.
There's like three variables.
But only two of them are actually genuinely variables. One of them is fixed at the start of the problem, so it's actually
Oh,
a
you
constant.
have a value?
Yeah, it's
Oh,
3,
okay.
yeah. We have a value R for our problem. So notice the difference between variables and parameters. I can choose different cones inside here, and that will change the h's and the r's, but the radius of the sphere will not change. What's that?
I was telling her that I brought that pretzels for her Spanish class.
There you go. Now, all of this is cool, but I actually think there's a slightly better way to mark things up here, because I end up with an uncomfortable expression. No, you're not the one I wanted. There we go. So I end up with an uncomfortable expression. Does everybody see this h minus r right here? This h minus r squared, which I'm going to have to like multiply out and all that, suggests that maybe I didn't pick the right variable. If I divide this up a little bit differently into the radius big R here, and now a small quantity that I can call y, and r like that, then I have the same thing but divided a little bit differently, and I have y squared plus r squared equals big R squared, and I have volume is equal to 1/3 pi r squared times y plus big R. So it may be that this would be a preferable way of dividing it up, and I'm not really sure yet until I get into the algebraic detail. So let's see. Let's first of all try this one. From this one I can solve for r squared. Does it seem profitable to simplify this? Can you see any advantage by looking ahead that we would simplify? Yeah, that's right. The r squareds are going to cancel out. So let me go ahead and simplify that. Negative 2hr plus positive 2hr minus h squared. Just like that. And that actually seems good enough. I think that this will work for plugging into here. Just like so. Any advantage to simplifying this? Yeah. Let's do that. Yes, sir.
Using R instead of B.
Yes, I wanted to get a general result so that I could use r equals 3, r equals 5, r equals 6, whatever, so that we could see the relationship.
Oh, okay.
Yeah. Yep. And so now now at this point we've got our relationship, we're ready for a derivative, dvdh, and this is going to give me now 4hr minus 3h squared is equal to 0. Set this equal to 0. These factors are irrelevant. I have a factor of h here that can be factored out. And I get two critical points. One of them is h equals 0, and one of them is h equals 4r over 3. We failed to do something before we got started. We failed to identify the domain. What is the smallest possible value for h?
0.
Mhm. And what is the largest possible value for h?
H. Oh, it has to be smaller than the diameter.
Yes, and the diameter is what in terms of 2r? That's right. So my domain for this problem is from 0 to 2r. So here's my v prime number line now. And I have a single critical point in the interior, which is 4r over 3. Just like that. And now it's fairly simple to check the signs of the derivative on either side. When, pick a number between 0 and 4r over 3. R works. That's 3r over 3, and so it's between 0 and 4r over 3. So r works, and when I plug in r into my factored form of the derivative right here, I get r times 4r minus 3r, which is going to be a positive value. Everybody see how I did that there? Yes, no? And now I'm going to choose a number that is larger than 4r over 3, but less than 2r. How about 1.5r? Something like that. And so when I plug in here, I'll get 1.5r, which is positive, times 4r minus, that would be 9.5r. It'd be bigger than 4r. And so we have a negative derivative right there. And because v prime is positive for all the interval to here, negative for all the interval to here, therefore we have a max. And we can say that volume of 4r over 3 is the max because v prime is positive for h less than 4r over 3, and v prime is negative for h larger than 4r over 3. Could we also have done a critical points endpoints analysis of this? Yeah, we sure could. But this is our flavor of the day, so we'll practice with it. What is that volume? We got to actually answer the question. Volume of 4r over 3. And it's 1/3 pi times, what do you have?
Negative h cubed. So it's 6h.
Sounds about right. That's going to give us 16 times 2 is 32 over 3. R cubed minus 64 over 3. Over 27, actually. R cubed over 9, you're right. Over 27 times 1/3. And so that's going to give me, let's see here, I need 3 of these, so I get 96 minus 64 is 32. Over 27, r cubed, times 1/3 pi, and that's 32 over 81 pi r cubed. Yeah, and you get 32 over 3 pi when r is 3. So what's the moral of this story? The moral of the story is that the actual calculus was not bad, but we needed a way to represent volume. So the key thing to pay attention to is how we divided it up. We had h, and then we went to the center and did h minus the radius right there, and that allowed us to do a nice little right triangle. Could we have also done it with the y? Yeah, we could have done it with the y, but I don't think we want to mess with the details on it. Okay, let's see what you do with this one. The trapezoid has three sides of length S. Show that of all such trapezoids, the one with maximum area has length of the fourth side of 2s. You guys can get into pairs and work this problem. Go.
Oh, was the S? I put 5.
So we want to quickly set up the trapezoid. And this group over here has done fairly well with that. What do you have for your trapezoid? It's hard for me to get my trapezoid in over here. That doesn't look very... That's pretty good. What happens down here, Charlie? How'd you mark this up?
Well, we mark it as 2s, so we can do that.
Can't do that, that's right.
So,
X.
Alright, so this is x, now what?
now we need the area.
Which is?
4.5 times s plus x.
Aha. Keep in mind that s is a constant in the problem. We do need to find h. So that's really the question, is what is that height h? And it sounds like the ladies over here have made some progress. Tell us what you got. Ah,
And so it's u squared plus b minus x over 2 squared, or I guess for x.
so this is x minus s over 2 here? I think that's right, because what you have is that x is composed of this guy plus this guy. Now you would assume symmetry, but that's actually legit because we have congruent triangles. Equals now s squared, and that's going to give you an auxiliary equation, and the rest should follow. So you should be able to carry it home from here. Keep in mind that s is not a variable, it's a constant within the problem.